So the next tutorial is on recent advances in stochastic convex and non-convex optimization by Ziyuan Allen-Zhu from Microsoft Research.
Thanks for the introduction. My name is Ziyuan, and I recently, actually 2 months ago, I joined Microsoft Research in the so-called machine learning / optimization group in the Redmond headquarters. So this talk is about recent advances in stochastic convex and non-convex optimization. As you can judge from the title, the talk is going to be divided roughly into 2 halves. The first half about convex and the second half about non-convex. So a few logistics. I'm going to give a 15-minute break in between whenever I finish the discussion about convex settings. And also, whenever I refer to a paper, I cite a paper in the talk. The paper's full title and so on can be found on the web page related to this talk, which you can use this barcode to find it. And also, after the conference, I heard that there will be video recordings online, and also I'm going to provide the slides as well. So if you missed any technical details, don't worry, like the talk will be online. Okay? Let me now start the talk, convex stochastic optimization. So pretty much in the first half of the talk, I would just focus on optimizing the following master problem. That is, I want to minimize the summation of 2 things. Psi, which is a convex regularizer, it can be either, say, the L1 regularizer or L2 regularizer on top of the variable vector x. And also, there exists a loss function. The loss function is a finite average over fi's. So I may have f1, f2 until fn. Each of them is a loss function, and I take an average over all of the loss. So in the first half of the talk, I would just focus on how to minimize this function fast. The reason I want to study this is because it arises prominently in machine learning. For instance, everyone knows support vector machine, maybe on the first 10 pages of any machine learning textbook. So here is a pictorial description about support vector machine. It's about how to find a separation, linear separation hyperplane that separates positive samples from negative samples. If you look at the training objective of support vector machine, you're going to get the following convex function. That is, you wish to minimize the average of the loss value of the so-called hinge loss values with respect to the data points, in which here I'm using AI to denote the ith data point, the ith feature vector, and bi to be, say, the label of the ith input. Now this quantity is the so-called hinge loss with respect to the current predictor x against the ith input data. So this is a loss function. And then I also regularize this with an L2 norm square. So this is the problem of support vector machine, and naturally it falls into this category of the master problem. And other problems that we are aware of include like ridge regression or lasso regression, which is, for instance, to do the squared loss with respect to the data points, and then we put an L1 regularizer in the front that encourages sparsity. So this is another example that falls into the master problem, and I can actually continue, but I will stop here. Also like logistic regression, like it's this loss function, you can put it here, it falls into this master problem. So this is the problem I wish to minimize as fast as possible in the first half of the talk. In fact, if you look at all of these 4 examples, you may realize that actually all of them are inside a very special class, subclass of the master problem. That is, each loss function here is actually a univariate function against the inner product between ai and x. And for this reason, in order to simplify some notations, I'm going to actually refer to this slightly smaller class of problems as the master problem, and I wish to minimize this one fast. Okay? So this at least includes all of these examples on the previous slide. So from a very high level, in the first half of the talk, I'm going to first introduce the primal, the dual, and the primal dual views of the same master problem. And on top of that, I'm also going to introduce smoothness and strong convexity assumptions on this master problem. Now we have roughly like 3 by whatever number of settings, and in each such setting, I wish to introduce solvers. That is, different algorithms that solve each individual subclass here. So that is the overview of the first half of the talk. I'm going to go into all of these 3 dimensions. Let me begin with the first dimension, which is the primal dual, and the dual view of the master problem. Before I do that, let me remind all of you about a very simple mathematical thing. That is the so-called Fenchel-Legendre duality theorem. So whenever we have a convex function, say gx, it could be of a d-dimensional space. Now the so-called Fenchel dual of this function is denoted by g star. And whenever I take input y here, then the value of g star at y is the maximization over all of possible x. Then you compute the inner product between y and x, then minus gx, and you maximize this function with respect to x. To give you a few examples, if we have the LP norm to the pth power as g, then its Fenchel dual becomes the q norm to the qth power if 1 over p plus 1 over q equals to 1. Therefore, like Euclidean norm, which is L2 norm square, is self-dual. So it is dual to itself. As another example, if we have a hinge loss like this, then you can also go into this mathematical definition and calculate that its Fenchel dual is of this form. So it's a function that is only defined on the interval between -1 and 0. And it's a linear function here, but otherwise it goes to positive infinity. Similarly, if you're given, say, the logistic loss, you can also compute its Fenchel dual. This time it becomes the so-called negative entropy function in the 1-dimensional space. Here, like the domain is between 0 and 1. So these are some typical examples of Fenchel duals. And the so-called duality theorem says that if you take the dual of the dual function, you get back the original function. That means if you take, say, the dual of this function, then you'll go back to the original logistic loss. Now, let me state a few properties about the Fenchel dual. The first property is that if the original function is convex, then the Fenchel dual is also convex. So I won't prove this to you, but pictorially, you see this is a convex function, and this is also convex on its domain. This is what I mean by proper convex functions. So the Fenchel dual is also convex. And the second property is that whenever we have the original function being smooth, then its Fenchel dual becomes strongly convex. Let me define what I mean by smoothness and strong convexity. So we say that a convex function is smooth if you take the Hessian, then all of the eigenvalues of the Hessian of the function are upper bounded by some parameter L. Whenever this is true, we say the function is smooth. Similarly, if a convex function is sigma strongly convex with parameter sigma, if all the eigenvalues of the Hessian are larger than or equal to a lower bound, denoted by sigma. And therefore, the second property says that if the original function is smooth, then the Fenchel dual becomes strongly convex, and actually vice versa. So again, I'm not going to give you a proof, but let me just prove it at least for the example above. In the example above, we have the logistic loss. If you take the second order derivative, because it's 1-dimensional space, the Hessian becomes a single value. And this value, if you plot it from, say, MATLAB, you can realize that this quantity is upper bounded by 1/4. And therefore, we can say that the logistic loss is a smooth function with parameter 1/4. In contrast, if you take the dual, which is the negative entropy, you can again compute its Hessian. This time, this value, you can verify that it's at least 4, because if you take y to be 1/2, this value is 4. And therefore, like, this negative entropy function is strongly convex with parameter 4. You see, like, 1/4 becomes 4, and this is an important property about Fenchel dual functions. Now, using this notion of Fenchel dual, we can talk about the primal dual views of the master problem. I'm going to call the original problem the primal view of the master problem. Now, using the definition of Fenchel dual, I can replace Fi with some new parameter yi, a real value, times ai transpose x, then minus the dual of Fi. If you maximize over y, then by the definition of functional dual, this gives you back the original function fi. Now, if you allow me to use the matrix A to denote the input data matrix, where each rows, the ith row is the vector ai, then I get back this saddle point formulation. To give you one example, if the original master problem is talking about solving this ridge regression, which has the L2 regularizer and the squat loss, then after this derivation from here to here, I get a saddle point problem that I wish to minimize over x and maximize over y. And here, the loss value, the loss function, which was squat loss, now it becomes its functional dual, which is of this form, and we also have this bilinear form like y transpose ax. So we call this the primal dual view of the master problem. If we do not stop here and use strong duality to actually swap this min and the max, so we move this minimization of x to here and the maximization to here, and then we put a minus sign in the front, now we can use functional duality again. Namely, we want to remove this maximization over x. The way we do that is to use the definition of the dual of this regularizer per psi. So if we have, so originally we have this per psi x and this bilinear form, we view that as a function over x. Now we maximize over x and we get back this functional dual with respect to the regularizer. So using this example again, here, originally we started with a quadratic minimization question with respect to x. Now we get back another quadratic minimization problem, but this time is with respect to the dual variables, the y vector. So we call this the dual view of the master problem. Okay? So this was actually first recorded, at least dates back to the paper of accelerated SDCA by Shalov, Schwartz, and Zhang, in which they wrote down this like full derivation from top to bottom. So if you want to know more technical details, feel free to go to any of these two references. And this captures the three equivalent views of the master problem: the primal view, the primal dual view, and the dual view. Let me now go to talk about smoothness and strong convexity. In this picture of the three different views, we can immediately realize something. If the original regularizer is strongly convex, according to the duality theorem, we know that per psi star, its functional dual, becomes smooth. And similarly, if the original loss functions are smooth, then I claim that in the other two views, fi star become strongly convex. So now if you stare at this picture for a while, you may immediately realize that there are four subclasses of the problem for each of the three views. For instance, in the primal view, we may have the function to be either strongly convex or not, either smooth or not. So we have 2 by 2, a total of 4 different possibilities. So each such possibility corresponds to one of those examples I showed on the first slide of the talk. For instance, for ridge regression, because we have L2 norm square, the objective is strongly convex. Because we have a squat loss, the loss function is smooth. And so on and so forth. Perhaps the hardest problem on this table is the L1 version of support vector machine, in which the objective is neither strongly convex nor smooth. So this gives rise to 4 different subclasses of the master problem in the primal view, and you can also do similar things for the primal dual view and the dual views. That totals into 12 different cases, and the general overview of the first half of the talk is for me to try my very best to illustrate a number of solvers for each of these 12 different views. So that's maybe an ambitious plan, but let me see if I can make it. So before I start to introduce solvers, let me make a very quick remark. So we have these 3 different views, and we know that to some extent, the 3 problems are equivalent. But in fact, if you start to design, say, first-order methods for these 3 different, using the 3 different views, you may realize that the methods actually have very different forms. For instance, we can try to do gradient descent on the primal view, which gives rise to algorithms that try to update the primal vector x. Say, in each iteration, I compute the gradient, I go in the direction of the negative gradient with some learning rate. This is gradient descent on the primal view. You can also do gradient descent on the dual view, like this, which is an update on the y vectors. So if you think about it, an algorithm that updates the primal vectors may not be related to an algorithm that updates on the dual vectors. And there's no generic way of transforming an algorithm from here to here. For this reason, designing algorithms for the three different views are actually completely different tasks. But on the other hand, if you think about it, because the three problems to some extent are equivalent to each other, therefore if you compute the final complexity of, say, this algorithm and that algorithm, maybe we should get the same quantity. So this is indeed true, and let me give you one example. Suppose we have this ridge regression. This is the primal objective, that's the dual objective, both being quadratic functions, but they're of different forms. So if you know a little bit theory about the convergence of gradient descent, you may have heard that gradient descent converges in a number of iterations that is proportional to the so-called condition number of the problem. The condition number is calculated as follows. You first compute the Hessian of the objective, which is this matrix. Then you compute its largest eigenvalue divided by the minimal eigenvalue. This is the so-called condition number. You calculate it, and this quantity characterizes basically how fast gradient descent converges in terms of minimizing, say, the primal objective. You can do the same thing for the dual. You get a different Hessian. This is like AA transpose, the other one is A transpose A. And this time, you can also compute the condition number, but in most of the cases, you're going to get actually the same quantity. So this looks different from above, but if you multiply the numerators and denominators, both by the same quantity, I think sigma times n, then you get the same fraction. So therefore, if we happen to be able to develop an algorithm, say for the primal view, perhaps we should be able to design an algorithm, say, in the other two views with the same complexity. So this is not only true for the first, the third one, but also here. Indeed, there exists a method called mirror descent that you can design for the primal dual view, which controls both a primal and a dual variable. It controls both x and y, and it converges in the same running time as the first and the second and the third method here. So this is about gradient descent and mirror descent. And in fact, in this full gradient setting, one can also do the so-called acceleration, which is known as momentum in our community. That is, we can do the so-called accelerated gradient descent. For instance, for the primal, we can do accelerated gradient descent for the dual. One can also do momentum for the primal dual view, but that results in like two different types of algorithms. But in all of these four, although the algorithms look very differently from each other, they happen to also have the same complexity, up to maybe at most a log factor. So therefore, like in the full gradient setting, without going into any details, we can classify first order methods into pretty much the following two categories. The first column have roughly the same complexity, and the second column have roughly the same complexity. So being accelerated methods using momentum, they naturally run faster than or equal to the first column. So this is a quick summary about full gradient methods, which is not the main topic of today, because today I want to focus on stochastic solvers. So for stochastic solvers, we again have primal, primal dual, and the dual views, but this time I claim there exist three different classes of methods. So from a very high level, the second class is going to be faster than or equal to the first class, and the third column is going to be faster than or equal to the second. So the most famous example in the first class of the methods is the so-called stochastic gradient descent method, Sc.D. Along with its variants, including like the Pegasus variant that works for strongly convex functions. So these are like examples of solvers in the first class. And for the second class, I claim that there exist two different set of algorithms. The first set of algorithms, based on the so-called variance reduction technique, which I'm going to introduce later, And they directly solve the primal. And the second class of methods, they are based on the so-called coordinate descent technique, which I'm also going to describe. They directly solve the dual. Let me give you a few examples. The so-called SAG, stochastic averaged gradient method, first proposed by Lorix, Schmidt, and Bach, was the first variance reduction-based method. And this method sits here. But unfortunately, it only solves a subclass of the master problem. And this issue has been later fixed by two independent works, one called SVRG and one called Saga. So these are examples of variance reduction-based methods, and they directly solve the primal. On this slide, by the way, I'm only going to name a few methods, but later, throughout the first half of the talk, I'm going to describe the technical details about these methods. So let me now just have a rough sense about where these names of the methods roughly sit in this 3x3 table. So these are some examples of variance reduction-based methods. They sit here, and they directly solve the primal. In the dual world, the very famous method called SDCA by Shalev, Schwartz, and Zhang, they utilize the idea of randomized coordinate descent to directly optimize over this dual objective. So this work is built upon the general framework of randomized coordinate descent, RCD, method by Yuri Nesterov, and it solves the full generality of all possible problems in this dual setting. So these two are like the two different classes of methods which sit, as you can imagine, because they sit both on the second column, they're going to have roughly the same total complexity, up to maybe at most a log factor. As for the third column, this is the column for accelerated methods, which are the methods that have acceleration, sometimes also known as momentum. So historically, accelerated methods were actually discovered in this direction. So the first accelerated method was actually developed for the dual objective first. That was, again, by Shalev, Schwartz, and Zhang. So they showed that there is a variant of SDCA in which they call accelerated SDCA that gives an accelerated convergence rate for the dual objective. But that method is not very easy to use. Therefore, later, there have been a number of ways to fix that. And most notably, the method of APCG provides a very simple accelerated coordinate descent method that solves all the generality of the dual objective. And I'm going to describe about APCG later. So these are examples of accelerated methods that work on the dual. Now let's go up. The first accelerated methods that work here are actually independently discovered by two groups of researchers. Zhang and Xiao from machine learning, and Xiao, by the way, is another researcher from our group in MSR Redmond. The other method, RPDG, was developed by Lan and Zhou from the operations research community. The two methods almost look the same to each other, and they both obtain an accelerated convergence rate on this saddle point, this primal dual formulation. Now finally, let's go to the primal. So it turns out that designing an accelerated method in the primal world is actually much, much more complicated than designing them for the other two worlds. In particular, the first such results were obtained by two reductions, the so-called APCG and catalyst reductions. So those are the results that roughly say the following. There exists a black box reduction. You don't even need to know what it is. As long as you feed into this reduction any method that sits on the second column, it automatically turns it into an accelerated method. So it sounds like almost perfect because it means that there's no additional work, thing you need to know. You just plug it in, you get an accelerated method. But unfortunately, those results only partially solve the acceleration problem on this block because, for instance, if you apply this reduction, you lose parallelism. So you can you can still do mini-batch to support parallel computations, but that does not converge very fast. So you lose also something like practicality, so you lose a bit. So these methods are still not perfect. So this year, finally, we proposed a method that's called Katyusha method, published in this year's Stock, in which we showed that there exists a direct method that directly solves the primal objective without any reduction, and it runs in an accelerated convergence rate. So from a very high level up to log factors, all of the methods sitting on the third column, they have roughly the same complexity. At this point, maybe you can already ask some question like, why do we have like 3 holes? So the reason is because like there isn't really such holes. In principle, you can, for instance, turn a method like SPDC to make it run slower. If you have a fast method, it's always possible to make it run slower. And if you do that, you can recover some methods that run like that behave similar to Sc.D sitting here or similar to SVRG sitting here. So these methods, I don't think they have been ever recorded, but in any case, I don't think they're interesting to study as well because we already have fast algorithms. Therefore, let's ignore that. One can also develop algorithms here, but let's not spend time into that. So for simplicity, let me pick one representative from each of these 6 different classes, and I'm going to introduce them in this first half of the talk in this order. I'm going to first describe Sc.D, then SVRG, then SDCA, then here, then go up. That is the plan of the first half of the talk. Good, so let me begin with Sc.D. Stochastic gradient descent. Suppose that we're minimizing this master problem, and for simplicity, let me assume that we do not have a regularizer. That is, we only have these loss functions. So we can, whenever you have an algorithm that works here, you can also turn it to work with a regularizer, but for notational simplicity, let me just ignore the regularizer and only call the loss function fx. And let's try to minimize fx. Here is the simple idea of stochastic gradient descent. That is, let us try to define the so-called gradient estimator of the function f, which says at any point x, we define the gradient estimator to be the gradient with respect to a random fi. Well, I is, say, uniformly chosen at random between 1 and n. So the gradient of f1, f2, until fn, we choose one of them at random. So this is, of course, an unbiased estimator to the full gradient of the function, but it is n times cheaper to compute, because computing the gradient with respect to one fi typically requires you to only read the ith input data without touching the entire data set altogether. But computing the full gradient requires you to really go through all the data, f1, f2, until fn, like all at once. So that could be very slow. So the idea of Sc.D is to say, let us try to move in the direction of the negative gradient estimator, iteration by iteration, like this. In the first iteration, remember we want to move in the direction of the negative gradient in order to decrease the objective, but we don't have time to compute the full gradient. Instead, let's try to randomly select an index I and go in the direction of the gradient estimator. It still gives us a rough estimation about where the minimal of the function is, and let's try to go there. So if you continue in this fashion, the algorithm may zigzag a little bit, because it's a randomized algorithm, it may not be very accurate. But mathematically, one can show that if you choose the learning rate of the algorithm appropriately, then Sc.D converges. This method converges in a rate that is written as epsilon proportional to 1 over root t. Here, epsilon is how close you get to the minimizer of the function, and the t is the number of iterations. This is what we say as the 1 over root t convergence rate. Or equivalently, you can write t equals to 1 over epsilon square, and therefore it's a 1 over epsilon square convergence rate. So this is the simple theory about Sc.D. Let me quickly point out an issue with Sc.D, that is, this gradient estimator, it is an unbiased estimator to the full gradient of the function. That is good, but unfortunately, the variance of this gradient estimator may be very large, even if our point x is currently very, very close to the minimum. Say that if x is x star, then my gradient of the function, of the full function f, is 0. But maybe my stochastic gradients, which are the gradient estimator, is with 1/4 probability here, 1/4 probability here, 1/4 here, 1/4 there. And therefore, like, although in expectation it equals to 0, it doesn't mean that the variance of the gradient estimator is small. So it turns out that there is a way to fix this. This is the so-called SVRG method, first independently discovered by Johnson and Zhang, as well as by John, McLavy, and Jane. So these two are different Johns. So the SVRG method assumes that each function fi is smooth, and then it starts to define the gradient estimator as follows. It first divides the algorithm into epochs. Each epoch of length m, which in practice, they suggest the value of m to be roughly 2 times the number of data points, 2 times n. Now, at the beginning of each epoch, let's call the current point x tilde and give it a name, call it a snapshot point. Now, whenever the algorithm is at a snapshot, it computes the full gradient of the function exactly. Okay? This takes a lot of running time because you have to go through the input data, you have to go through all of the input functions, f1 until fn, like all at once. But fortunately, you only do this very rarely, or you only do this at the snapshot points. And therefore, like if the epoch length is proportional to the number of data points, then in the average sense, you're only computing still like constant number of gradients like this per iteration. So it's not a big deal. Now in each follow-up iteration, SVRG defines the gradient estimator to be, first you read the full gradient of the most recent snapshot, which you have already computed. You load it, you save it in the memory and you load it out. Now you make a simple change on top of that. Namely, you subtract this vector by the gradient with respect to a random fi at the snapshot point x tilde, and then you add it by the gradient with respect to the same fi at the current point xk. So in this way, this new gradient estimator, you can verify that it is still an unbiased estimator to the full gradient of the function because this quantity has an expectation of 0. But fortunately, this new gradient estimator has a variance that approaches to 0. So here is the reason why. When the algorithm approaches to the minimum of the function, then both xk and x tilde approaches to x star. And whenever this happens, we know that these two black terms will become closer and closer to each other, and therefore this term and that term will also be closer to each other. So this makes sure that the variance of this gradient estimator truly approaches to 0. So using this idea to reduce the variance, one can show that this method, SVRG, converges in a rate that is 1 over t, which is better than 1 over root t for stochastic gradient descent. So this is a very quick one-page summary about the Sc.D and SVRG. So before I proceed to talk about other methods, let me quickly make 2 remarks. One is about the strong convexity and smoothness assumptions. When I described, remember that we have 4 different cases. The master problem can either be strongly convex or not, smooth or not. So 4 different cases. In fact, when I described the Sc.D method, I did not impose any assumption. I didn't say it's smooth. I didn't say the objective is strongly convex. And therefore, the original proof of Sc.D directly works for case 4. It sits here. But you can actually go into data analysis to make it also work for the other 3 cases. So here, like this parameter g is an upper bound on the norm of the gradient. So this is the convergence rate of Sc.D. Now, if you move it to the left, Sc.D also works with additional assumptions. Like whenever you have more assumptions, it's only getting better. And indeed, the convergence rate becomes 1 over t in the first 2 cases, and it remains to be 1 over root t in the other 2 cases. Therefore, like if one asks me about what is the true convergence rate of SGD, I will say it depends. It depends on whether or not you're in case 1, 2 or case 3, 4. You may either get 1 over t or 1 over root t. Similarly, for SVRG, the original proof of SVRG actually works in case 1. It gives a so-called linear convergence rate in this case, meaning that the error epsilon actually grows exponentially small in terms of t, the number of iterations. So this is very good, and this is also why that we say SVRG works better than SGD, not only in theory, but also in practice. So one can also ask how to turn this result into the other 3 cases. For instance, one can make SVRG also work in case 3, and the best known result is of this form. So as you can see that t is proportional to 1 over epsilon, and this is known as 1 over t convergence rate, and this is indeed faster than the 1 over root t convergence rate of SGD. And this is why that SVRG also performs better than SGD in case 3. But unfortunately, SVRG, although it also works for cases 2 and 4, which are the cases when the objective is not smooth, it still works, but unfortunately the complexities you're going to get does not actually outperform SGD. It almost matches SGD, but it's slightly worse. So for this reason, throughout this talk, in fact, whenever I talk about one method, I sometimes make assumptions, say that maybe I assume it's in case 1, but it doesn't mean that the method does not apply to other cases. So one can always do the typical analysis to somehow convert one result into others. So there are a few ad hoc ways to do that, but there are also generic techniques for you to do, for you to convert a result from one case to some other case. For instance, whenever you have a result for case 3, you can repeatedly restart the algorithm by changing the learning rate to make it smaller and smaller. And therefore, one can always turn a result in case 3 into case 1. And last year with Allen-Zhu, we showed that there exists reductions in some optimal sense in which one can turn an algorithm in case 1 also into the other 3 cases. So for this reason, although papers are sometimes, the theorems are sometimes proven only for one case, but implicitly it also works for other cases as well. So that is my first comment about the strong convexity and the smoothness assumptions. My second comment here is about some detailed specifics about SVRG. We know that SVRG divides the algorithm into epochs, and the practical suggestion was to choose the epoch length to be a constant number times the number of data points. So in fact, one can ask, can we actually vary this epoch length to get an even faster running time? So the answer is really yes. In particular, if the original function is not strongly convex, which corresponds to case 3 in the previous slide, in this case, the suggestion is actually to make the epoch length to grow exponentially. So it starts with maybe, say, n, and then in the next epoch, let's try to make it 2n, then 4n, 8n, and so on. So this turns out to be a better way to choose the epoch lengths. On the other hand, if n, the number of data points, is huge, then whenever I talk about SVRG with some experimentalists, I often get the following feedback. They told me that SVRG is so slow because computing the full gradient requires you to go through the input data set, all at once. That requires, I don't know, maybe a minute if we have, say, 1 million of images. That could be very slow. But my reaction is always if n is really very huge, then maybe you don't need to have an epoch to be that long. You can, for instance, recompute a gradient on the snapshot. You can redefine a snapshot whenever you finish reading, say, 1% of the input. And whenever you finished 1% of the input, then you can try to define the gradient estimator to be, you can try to, instead of computing the full gradient of the function, which requires you to read everything, you can try to estimate this full gradient by just reading 1% of the input. So this sounds like some heuristics to reduce the epoch length, but in fact, it also works with very nice theoretical support. So for those of you interested in this parameter regime, you can look at the paper by Lei and Michael Jordan. That's a paper published in this year. So that's my second comment about SVRG. That is the epoch length, although I wrote it as a constant times n, but you can really make it change for specific, for different settings. So that finishes the quick summary about stochastic gradient descent and SVRG. Let me now move to coordinate descent. First of all, what is coordinate descent? I claim that it's a very different type of method comparing to stochastic gradient descent. In the stochastic case, such as Sc.D, we assume the objective is a finite average of fi's, and then in each iteration, we try to move in the direction of the negative gradient with respect to a random fi. So this is stochastic gradient descent. But in contrast, in the so-called coordinate descent case, we do something very different. First of all, we do not assume any assumption that the objective is a finite average. At the same time, in each iteration, we move from xk to xk plus 1 by only changing one coordinate. This is the random coordinate I drawn, say, uniformly at random from all the coordinates, and we only compute the ith coordinate of the full gradient of the function, and then we only move in that direction without touching any of the other coordinates. So this is coordinate descent. As you see, like, this I sits here because it's the ith component of the vector, but the I sits here because it's the ith component of the fi's. So they have very different behaviors. Pictorially, coordinate descent says that whenever this is, say, the negative direction of the gradient, then let's choose a random coordinate. It can be either, say, the x coordinate, the y coordinate, and then let's try to move in the direction of one of the two coordinates. But stochastic gradient descent is saying that let's try to randomly select a vector whose expectation equals to the, say, the negative gradient of the function. And as you can see already from these two pictures, there is a very different stability effect difference between the two methods. On the right-hand side, regardless of which coordinate you pick, according to the definition of gradient, there always exists a step length in which you can decrease the objective. Either you move up, you move left. There always exists a step length in which you decrease the objective. You can always decrease that. So this is very stable. It means that the algorithm is always making progress. But in contrast, for stochastic gradient methods, if at some point you're not lucky, you picked a direction that is, like, say, going in this way, then you may not necessarily decrease the objective in this single iteration. In other words, stochastic gradient methods are actually much harder to design and analyze than coordinate gradient methods. Okay, so this is the pictorial way to describe coordinate descent. Let's now move here to talk about SDCA. So what SDCA did in the paper is actually a general theory about coordinate descent. It says that whenever you have a convex function, say gy, let's assume that each coordinate of g to be L smooth with parameter L. This means that if you take the Hessian of the function, you compute it at any point, you look at the ith diagonal entry of the Hessian. We know this is the real value. By convexity, we know this real value is non-negative. But at the same time, let's assume that the entry is upper bounded by some parameter L. This is the so-called coordinate smoothness of the function. Once we assume the coordinate smoothness, we can start to talk about a very simple algorithm. That is, in each iteration, we try to move in the direction of the negative coordinate gradient with respect to a random coordinate I, with the step length just being 1 over L. Period. So that's the algorithm. So this algorithm turns out to converge very well. And if you go into the theory, you can see, like, the number of iterations for it to converge is proportional to the number of coordinates, which is the dimension, also proportional to the smoothness parameter, but with this 1/epsilon convergence rate. Okay, so this is the simple theory of coordinate descent, for instance, using the paper of SDCA. If on top of that, you also assume that the function is strongly convex, then this convergence rate becomes a linear convergence rate, but at the same time, you pay in this denominator the strong convexity of the function. So this is the simple theory about coordinate descent, and let's see how we can use it to solve our master problem. Remember, the master problem is this. It's a primal problem, and if we turn that into the dual, we have to recalculate what is the coordinate smoothness and what is the strong convexity. Namely, if the original problem, say, is sigma strongly convex and, say, L smooth, then when you go to the dual, remember, like, psi star becomes 1/sigma smooth, and the Fi star becomes 1/L strongly convex. Now, if you call this function g, you can calculate precisely what is its coordinate smoothness and strong convexity. Believe me, you're going to get this quantity. Okay, the extra factor of, say, 1/n square is because you have a 1/n sitting here, and therefore, like, this is the coordinate smoothness and strong convexity. Now, if you plug this into the formula above by replacing L with this parameter, replacing sigma with that parameter, and also pay attention that the dimension here is actually n because we have n dual variables in the dual formulation. So y is of n-dimensional space, and therefore this d becomes actually n. And therefore, like, you plug in the general theory together with the parameters, you get a number of iterations. And this value, if you calculate it, it actually matches precisely the number of iterations of SVRG that sit over there. Okay? So not only that, also the per iteration complexity of computing the coordinate gradient also matches the per iteration complexity of, say, Sc.D or SVRG. And therefore, that we truly have that SDCA sits here, it has up to, I think, only constant factors, the same complexity as SVRG. So it really sits here. Now we can, again, ask ourselves questions like, how does SDCA perform in the other three cases? So, of course, you can imagine that it should match the performance of SVRG here, and at the same time, it gives you a running time that matches SVRG here, but does not actually outperform Sc.D. So this is a very quick summary about SDCA, which is a dual coordinate descent method that directly solves the dual. As you can see, that SVRG is actually very hard to describe because I have to define the gradient estimator, the variance, and so on. But in contrast, in the dual world, actually designing a coordinate descent method is very, very simple. So this is really because coordinate descent has the stability that helps us to, make sure, like, the algorithm always makes progress per iteration. But in contrast, a stochastic gradient method does not have that property. And therefore, designing primal methods are actually harder tasks. Let us now move to APCG. So APCG is an accelerated method on top of SDCA. First of all, what is acceleration? In the full gradient setting, remember that if we have a convex function that is smooth, then we can either do gradient descent that looks like this, or something called accelerated gradient descent. It converges quadratically faster than gradient descent, and here is how it works. Using the original momentum view of Nestrov, in the first iteration, let us also try to go in the direction of the negative gradient, the same as gradient descent. But from the second iteration on, we not only move in the direction of the negative gradient, we also try to move in the direction called momentum, which is how much we have moved in the immediate previous iteration. And then we call this new point x2, and we move there. In the next iteration, the third one, we do the same thing. Negative gradient, momentum, and so on. So somehow magically, one can show that this momentum-based method converges in a rate that is quadratically faster than gradient descent. So the picture is probably very good in terms of explaining the algorithm from a very high level. But if you think about it, why could momentum help? And why does it help by improving the convergence rate quadratically instead of, say, improving it by a constant factor or even cubically? So in fact, the mathematics behind the convergence rate for any accelerated method is pretty non-trivial. And there exist a few different ways to prove that. Like, for instance, Nesterof's original potential function view. There also exists like differential equation proofs to show why this method converges quadratically faster. And there's also a geometric proof using ellipsoid method. And I personally prefer the so-called linear coupling view, which re-explains momentum as a linear combination of a gradient descent and a mirror descent method. So if you're interested in why acceleration works in the full gradient setting, you're encouraged to read any of the 4 papers, 4 like lines of research here, and that can give you a mathematical proof. But I won't talk about that today. Instead, I will just define APCG using this picture, this momentum picture. It does acceleration on top of SDCA. Pictorially, in the first iteration, it tries to move in the direction of a negative coordinate gradient with the coordinate I chosen uniformly at random, the same as SDCA. But from the second iteration on, it not only goes in the direction of a random coordinate gradient, it also tries to move in the direction of momentum, which is how much I have moved in the previous iteration. And I keep going just like this. Negative coordinate gradient, momentum, negative coordinate gradient, momentum, and so on. So one can show that this method works. The proof is actually very analogous to the full gradient setting, and the general theory says that if you have a function that is, say, L coordinate smooth, and also, say, sigma strongly convex, then the non-accelerated method of SDCA converges in this number of iterations, but if you do acceleration, which is if you do this like green momentum as well, then it converges in this number of iterations. You see, like, the parameter, the dependency on L and sigma become quadratically better, but the dimension n, if you have n coordinates, then the dimension n actually stays the same. So this is believable because think about it, if you have a coordinate method, you need to at least touch all the coordinates before you can make any progress. And therefore, the linear dependency on n should still stay here. So this is the general theory about accelerated coordinate descent. Let us now see how to apply that to the master problem. So the master problem is on the primal side. And as we have already argued, if the original problem is, say, sigma strongly convex and L smooth, then you can calculate that the dual objective here becomes this coordinate smooth and this strongly convex. Now you plug this into the general theorem about APCG. Now you get a number of iterations. And I claim that this is the result you are going to get. As you can see, like from this formulation, it looks very differently from the complexity of, for instance, SVRG and SDCA. And this is why accelerated methods have sits in the third class. So this is the first class of method. This is the second class of complexities. This is the third class. So it sits in a different class that has a very different complexity comparing to SDCA. So if you allow me to use the so-called O tilde notation to hide log factors, then I can remove the log factors and write things more concisely. In this way, I get more space, so I can finally put in the complexity for these two. Otherwise, I don't have space. So the complexities for both SVRG and SDCA are actually of this form for cases 2 and 4. And this is why I said they do not run better than Sc.D. Okay, because of the additional additive term n. But fortunately, APCG applies also to the other 3 cases, and this is the complexity you're going to get. T, again, is the number of iterations. So I claim that if you stare at this table, all the quantities in the middle are larger than or equal to all the quantities below, pairwise, like respectively. Did anyone see why? That's because a plus square root ab is less or equal to 2a plus b, which is less or equal to order of a plus b. And therefore, although it seems to have a square root n dependency here, like on the numerator, but in fact, this quantity is less than or equal to the quantity above. So this means accelerated methods run faster than non-accelerated ones. Not necessarily than like Sc.D here and here, but at least like faster than everything in the middle. To give you one example, if in case 3, you compute the complexities in theory, this is what you're going to get. So Sc.D has a convergence rate that's 1 over epsilon square. SVRG is better. It has 1 over epsilon convergence, but APCG has the 1 over square root epsilon convergence, which is the best. And the two methods of SVRG and APCG, they touch at the same point of t roughly being n, and the APCG becomes faster than SVRG, and which in turn is faster than Sc.D. So when I was preparing for this talk, I was trying to look for also an empirical curve. So I found out definitely curves in which matches this black versus the red, which we're also going to see some examples today. But unfortunately, I cannot find a picture that contains all the three, and therefore just believe me, this also works in practice. Okay? So that's an illustration about this APCG result, which is an acceleration on top of coordinate descent. Let us now move upward to talk about, on a single slide, very concisely about how SPDC works. So SPDC is a method that works on the primal dual formulation. That means the algorithm has to keep track of two vectors per iteration, a primal vector and the dual vector. So it keeps like both vector in the memory. And then the idea of SPDC can be essentially stated as follows. In each iteration, let us try to do both a coordinate descent on the y vector as well as a gradient descent on the x vector. To give you one example, suppose we do not have these two terms, just for notational simplicity. Suppose we only have this bilinear term, y transpose ax. Now what they proposed is to perform a coordinate descent on y by moving in the following direction. You compute ax, which is the derivative of this bilinear form with respect to y. So therefore, the gradient is ax up to the constant factor 1 over n. Now you have this vector, but you only take one coordinate out of it, which is n times cheaper to compute because you only take the ith row of the matrix interproducted with x. So you compute this value and you only change y by one coordinate. This is the coordinate descent step on top of y. But on the x side, you do a full gradient descent. You compute the full gradient of A transpose y, and then you you move your x in the direction of the negative gradient with some learning rate on x, which doesn't necessarily equal to the learning rate on y. So now the main contribution of SPDC is to introduce momentum on top of here. That is, instead of computing ax, let us try to compute a times xk plus xk minus 1. So this is momentum. That is, I not only compute my gradient with respect to the current point, but I also add on top of that momentum, which is how much I have moved in the most recent iteration. So from a very high level, this picture describes SPDC, and using a very non-trivial proof, one can show that SPDC converges up to log factors in this, it has the same complexities as APCG. So this is a very quick summary about SPDC. In the very end, let me go to the primal side to talk about how to do acceleration directly on the primal. As you have already seen, momentum was actually the key to make acceleration work for both the dual word and the primal dual word. Now, can we do momentum on the primal? It turns out that the answer is not quite. There exists actually counterexamples, and let me use one picture to illustrate why. If we apply, say, either Sc.D or SVRG, so any primal stochastic gradient method, then because the method is randomized, it doesn't, the direction that we move doesn't necessarily equal to the direction of the true gradient, then the algorithm may zigzag, as the time goes. Because it zigzags, at some point we may make mistakes, meaning that we might move in a direction that does not, maybe x star is here, but we move in a direction that is not towards x star. Whenever this happens, think about it. Whenever you also do momentum, the momentum says, I am going to play whatever I have played in the previous iteration. That means this mistake will be repeated twice. Even worse, momentum says that I'm going to play whatever I have played in the previous iteration. In that iteration, you have already played what you have played in the two iterations before. That means this same mistake, informally speaking, will be repeated actually a number of times before the memory somehow fades away. So because of this issue, then directly applying momentum on top of, say, either Sc.D or SVRG does not give significant, does not give at least in terms of theory, in terms of the worst case, it does not give any better theoretical running time. And this was indeed analyzed, for instance, by Nintendo, in which he showed that if you do, say, momentum on top of SVRG, you get an algorithm, but even if you tune the parameters very well, like for the momentum and so on, it doesn't even outperform SVRG, at least in the worst case. So another way to see this issue is that, remember, in the coordinate descent case, coordinate descent is a very stable algorithm. It never makes mistake. Regardless of which direction you pick, you can guarantee to decrease the objective. But in the stochastic case, you do not have this property. You may actually move in the wrong direction. So this is why applying momentum alone does not really help you to get faster algorithm, even for convex functions. Therefore, let me introduce something else. This is what we call the Katyusha method. It works as follows. In the first iteration, we still go in the direction of the negative gradient estimator, the same as SVRG. From the second iteration on, we first move in the direction of the negative gradient estimator, and we also move in the direction of Nastrov's momentum. But we don't stop there. We call this point a green point, and then we connect it with x0 and find its midpoint. Call this new point x2. So this is like putting a very strong magnet on top of x0 and say that wherever you go, don't forget to come home every iteration with a weight 1/2. So I continue in the same fashion. I go negative gradient estimator, momentum, retract. Negative gradient estimator, momentum, retract, and so on until every m iterations I move the magnet to the new point. Remember, m is the number of is the length of the epoch for SVRG. In terms of defining the gradient estimator, it's defined. The snapshot is updated every m iterations, and it's the same m. Every m iterations, I move the magnet to this new snapshot, and I continue from there. I do not restart. I continue from there. That is, I do negative gradient estimator, momentum, retract, and so on. So I call this orange arrow the Katyusha momentum to distinguish it from the original Nastrov's momentum. So one can show that this method works. So for instance, these are the experiments with respect to, I think, MNIST, RCV1, and the cover type, or maybe RCV1 cover type. I forgot the 3 different data sets from LeapSVM. As you can see, SVRG is the red curve, it converges. But SVRG plus momentum is the black dashed one. It sometimes gives you very good performance, but not always. There exist data sets in which applying momentum, even if you directly applying momentum on top of SVRG, even if you tune the parameters very hard, still you cannot beat SVRG by too much. But instead, if you use this Katyusha momentum as a fix, then you can start to experience really accelerated convergence rate. To sum up, less is more. Sometimes stabilizing the algorithm makes the algorithm run even faster. In other words, the original momentum does not always work for the stochastic setting. even for convex and offline problems, not to say non-convex ones, which I'm going to talk about in the next talk. And this Katyusha momentum works for stochastic gradient methods for actually SVRG, at least for convex and offline problems. So this summarizes this SVRG, this Katyusha method, and it gives the same type of complexities, and they directly solve the primal. And even more interestingly, if you spell out the log vectors, Katyusha also matches the best possible log vectors in terms of the dependency on epsilon. For instance, Katyusha gives the 1 over root epsilon convergence here, but in contrast, other algorithms give like at least log 1 over epsilon over square root epsilon, so they lose some log vectors. But Katyusha like matches this optimal convergence, as shown by like Woodworth and Cerebral in last year's NIPS. So this is my quick summary about this Katyusha method. So at this point, let me raise actually 3 questions. The first question is, we have 3 different views. We have the primal view, the primal dual view, and the dual view. But how do we select from the 3 views? Is one of the 3 like significantly better than the other 2? That's my question number 1. Question number 2, how do we select from the 3 classes of methods? When should we use acceleration in particular? And question number 3, how do those methods scale if we have parallelism? If we have, say, 1,000 machines, then can we speed up the performance of any of these methods by a factor of 1,000? So at the beginning of the second half of the talk, I'm going to answer such questions, and then I will move to the non-convex setting of stochastic optimization. So let's have a quick break. So what time is it? It's 4:08. Let's meet at, sorry, it's 2:08. Let's meet at 2:20, if that's okay. Let's start at 2:20. Thanks. All right, so let me now start the second half of the talk. I will begin by first answering the 3 questions I left at the end of the first talk. That is, the first question is, how do we choose between primal, the primal dual, and the dual? So here is my, so first of all, let's remember that in each of the 3 views, we have 4 different classes of problems, depending on the problem being strongly convex or smooth and so on. And because of the functional duality, say a strongly convex thing means like a strongly convex regularizer means that, sorry, this is strongly convex in X, and a smooth loss function here means a strongly convex in Y, and so on. So vertically, like those 4 cases correspond to each other. So let's recall like this picture. And now let me start to throw out my 2 cents. That is based on my own experience about using these methods like SVRG, SPDC, and so on. So I claim that in case 1, in the first case, it actually doesn't matter. You can either choose the primal or choose the dual, but I would not recommend you to use the primal dual view. So here's the reason. In the primal dual view, we have to both maintain an X and a Y variable because it's a saddle point formulation. And therefore, in principle, you have to tune both a learning rate for the X variable and a learning rate for the Y variable. So this gives some additional parameter tuning difficulty. So I have friends who told me that at least for like, for instance, case 1, applying SPDC is really not very pleasant because of the tuning. But instead, if you do the primal or do the dual, you only need to tune 1 parameters. That is good. So for case 3, my personal recommendation is to do the primal. The reason is because on the dual side, if you look at here, the objective is not smooth. But if you remember that whenever I mention about coordinate descent and accelerated coordinate descent, I'm assuming the function to be coordinate smooth. Therefore, if you do not have coordinate smoothness, then in principle, to apply such methods, you can still apply them, but you have to first smoothen the objective. This gives another dimension of parameter tuning, which means that the practical use of such methods may not be very pleasant. And therefore, I do not recommend of using a dual method here. And also, I do not recommend of using a primal dual method here. Symmetrically, for case 2, I would recommend of using a dual solver, like APCG or SDCA, but not on the primal. Because on the primal side, the objective is not smooth, and therefore to apply SVRG or Katyusha, one has to first smoothen the objective. For similar reason, that gives that requires one more dimension of parameter tuning. But interestingly, for the case 4, based on my experience, I would recommend actually the primal dual solver. So here's the reason. In the primal and dual side, both problems are non-smooth, and therefore one needs one extra dimension of parameter tuning. Therefore, if you already need that extra dimension of parameter tuning, why don't you use a primal dual solver, which requires like 2 parameters to tune, but at least because you can directly solve this objective, you don't need the smoothing step, so it runs actually very well in practice. And therefore, like, this is my personal recommendation about how to choose between the primal, the dual, and the primal dual solvers. That is, it really depends on which subcases you are in the 4 different settings. So everything will be, on the slides will be on the website. So in case you didn't catch that, it's all right. And in fact, there are even more complicated settings. For instance, sometimes each Fix may not be of the simple form that is Fi. That is a univariate function, so this is the inner product between AI and X, which is true for support vector machine like ridge regression and so on, but in general, one may face problems that are not of this form. And whenever this is true, then I would recommend using a primal solver because the dual problem actually becomes very high dimensional. So this is no longer an n-dimensional dual vector, it becomes n times d dimensional. So whenever this happens, I would recommend the primal solver. And also, as you will see, like very shortly, when we go into the non-convex world, meaning that each function Fix is not convex, whenever this happens, we don't even have a dual. And therefore, we are forced in these settings to study the primal. So therefore, like the primal setting also has advantages, at least whenever one of these 2 happens. So that's my summary about the first question. Now let's go to the second. When do we use, for instance, acceleration? Just by looking at these complexities, we can already conclude that whenever we have a very small epsilon, whenever we need a very high accuracy, then we want acceleration because these results have better epsilon dependencies than these results. At the same time, whenever we have small, strong convexity parameters, we more want to use acceleration because the sigma dependency here is better than that. So this is also confirmed in practice. For instance, this is a picture from the paper of APCG. Well, they showed that the smaller the regularizer, the L2 regularizer is, meaning that the smaller the strong convexity is, then the more desirable you want to use an accelerated method like the red curve. But instead, if you have a very strongly convex function, then sometimes doing acceleration like APCG doesn't give you much. It runs roughly the same as SPDC. Therefore, from a very high level, smaller epsilon encourages us to use acceleration more, and the smaller delta encourages us to use acceleration more. But whenever I talk about this to my colleagues or experimentalists, they often react as follows. For machine learning tasks, do we really need epsilon to be so small? Do we really need a very high accuracy? Maybe already epsilon to be, say, 10 to the -3 already suffices in terms of, say, classifying data. So here is how I responded whenever I got such a question. That is, nowadays we have more and more machine learning tasks that require us to apply stochastic solvers repeatedly. For instance, in this ICML, my co-author will actually present, he will present 2 talks, one on Tuesday, actually both on Tuesday, in which for both problems, we need to repeatedly apply ridge regression, say roughly 100 times in practice. So this means whenever we have an arrow, say for the first application of ridge regression, this arrow is going to be propagated to the input of the second ridge regression, and then so on and so forth. So if this happens, we really need accuracy to be very high, and therefore accelerated methods really are also interesting, especially when we are doing applications like this. So that's my answer for the second question. For the third question about parallelism, that is, how do at least this method scale if we have multiple machines? More precisely, whenever we talk about a stochastic method, we have computed the gradient with respect to just the one random Fi. But if we have, say, B different machines, then we can actually compute the stochastic gradients with respect to B different random choices of I. So this is known as the min-batch setting of stochastic gradient methods. Now a very natural question arises. Suppose in each iteration, I am allowed to use B different stochastic gradients, then does the total number of iterations get improved by a factor of B or not? Let me divide this into 3 cases. Sometimes the algorithm, if this is the total amount of work, the number of iterations, if I use one machine, but if you use B different machines, sometimes the algorithm does not scale well, meaning that the total number of iterations does not get improved. This is the first case. No parallel speedup. The best case would be like if we divide the work into B different machines, then the total number of iterations you need also divides by a factor of B. This is known as linear parallel speedup if we ignore the communication overhead. And sometimes we may have something sitting in between, meaning that if you have B machines, things scale up by a factor that's not 1, not B, but something in between. So it turns out that, first of all, stochastic gradient descent sits here. So this is good. And the fundamental reason is because if you look at the convergence rate for Sc.D, it depends on this parameter G, which is the variance of the stochastic gradient estimator. And this variance, by the law of large numbers, it decreases by a factor of B whenever you randomly sample B different independent copies. And the variance decreases by a factor of B, and therefore Sc.D really sits here. It has linear parallel speedup. Up to B less than or equal to root n, there's a lower bound, and B cannot really go better than that, but that's enough. Like if n is, say, 1,000,000, then you can already divide the work into, say, 1,000 different machines. So this is already good. Unfortunately, most of the non-accelerated methods sitting in the second column actually sit here. They have no parallel speedup whatsoever without additional assumption. The fundamental reason here is because, for instance, SVRG, if you remember, this is the number of iterations. It has like n plus something. But now, if you start to do mini-batch, only the first term get divided by the factor of B, but not the other term, which typically is the larger term. And therefore, without additional assumption, SVRG and SDCA and so on, these methods do not have any parallel speedup. Katyusha, it sits here. It does have a similar linear speedup performance compared with Sc.D, as well as like SPDC, recently shown by Shibagaki and Takuichi this year, as well as another accelerated method, which is similar to Katyusha, by Murata and Suzuki. So these methods enjoy linear parallel speedup. But unfortunately, some other accelerated methods, such as like Catalyst and APPA, they only enjoy like partial parallel speedup with some fundamental issues sitting there. This is why I said, like, using this kind of reductions, yes, you can get accelerated methods, but you're going to lose something. And this is precisely one of the places we lose, so we cannot get good parallel speedup. And other methods, such as APCG, it currently sits here. But I personally believe that one can eventually move APCG here. I didn't spend any time on this, but If you have any idea how to prove it, feel free to let me know, or write a paper, then let me know. So I do believe APCG should sit here, but there are fundamental issues that really prevent these methods from going to the right and these methods from going to the right. So this answers my third question, and this finishes the convex problem of the convex discussions about stochastic gradient methods, and I actually covered 4 dimensions. Let me now go to the second half of the talk about non-convex optimization. So in the non-convex world, pretty much everyone asks the same question, that is non-convex optimization really hard? So on one hand, it is hard because there exist functions that even finding local minima is NP hard. So NP hard is really hard, this we know. But on the other hand, sometimes non-convex problems can be also easy to solve. A very famous example is the problem of finding the minimal eigenvalue of a symmetric matrix. For this objective, even just the numerator is not necessarily convex, because the symmetric matrix A may have negative eigenvalues, for instance. But still, we know how to find minimal eigenvectors, and this problem is efficiently solvable. For this reason, pretty much most of the non-convex optimization research has been in between. That is, not to solve the most general problem, and then not to solve very specific problems, but try to solve something in between. In this talk, I'm going to summarize most of the research in non-convex optimization into the following 3 categories. The first category is the type of research that reformulate the problem to make it convex. The second category is the category of results in which they try to exploit what I would define to be the one-point convexity of the function. And the third category is the type of results that will find, instead of exact local minima, but approximate local minima or approximate stationary points. So I will spend most of my time in this one, but I will also quickly mention the other 2. Let me begin with the simplest one, about reformulation. Pretty much like for each different problem, there may exist a different reformulation. So one just needs to be clever and creative. So to give you one example, this minimization of the eigenvector problem can actually be turned into convex optimization using the so-called shift and invert reduction. One can find the references from Gabriel et al. And the references therein. So this reduction, from a very high level, it says that in order to find minimal eigenvector, it suffices to do convex optimization. That is to repeatedly compute the minimizer of a quadratic function where lambda is a real value that is guaranteed to make sure like the matrix here is positive semi-definite. So A minus lambda identity is positive semi-definite, and therefore this is a convex function to minimize. Now this framework is saying that in order to solve the original eigenvector problem, it actually suffices to do convex optimization. And we of course know how to do convex optimization, we even know how to do SVRG here. And therefore like the eigenvector problem, although it looked like a non-convex problem, there exist ways to reformulate it to make it convex. So this is also true, for instance, for finding the top k singular vectors and so on, we showed last year. And that's the only thing I want to say about this third box here, because it really depends on the problem you're facing. Like, you just need to be creative and sometimes to come up with a way to reformulate the problem. There's no generic technique I can describe in this talk. For the second type of results, they exploit what I'm going to define to be the one-point convexity of the function. Let us recall that whenever a function f is convex, we know that between any 2 points, x and y, they satisfy the following inequality. Okay? Therefore, a natural question here is that if we are facing a non-convex function, can we also somehow prove that the function satisfies this inequality, but with respect to only 1 point? That is, for all x, but with respect to the global minimum. So sometimes we can maybe expect the function, although being non-convex, but still it is somehow one point convex with respect to the minimum of the function. And whenever this is satisfied, the function does not necessarily need to be convex. So this is a weaker assumption than assuming the function to satisfy this, and alpha can be an arbitrary constant between, say, 0 and 1, not including 0. So when this holds, then we can start to ask ourselves, can we design an algorithm that works under this type of assumption? So this is one way to define one-point convexity, but there are actually many more other ways. For instance, if the function is strongly convex or smooth, classically, people know that the function has to satisfy some additional properties like this. One can find them, say, in some convex optimization textbooks. Now we can ask similar questions, which is if we generalize such properties to let them become assumptions on non-convex optimization, then whenever we are facing a non-convex problem, can we somehow prove that the objective satisfies one of these 4 properties? If so, can we design an algorithm that, say, converges to X star under these assumptions? Okay? So this is the general framework about exploiting what we call the one-point convexity of a non-convex function. So indeed, by the way, like, I don't actually personally know good names for these assumptions. I called all of them one-point convexity. What I know is that the third property is also called the Polyak-Lajasiewicz condition, and I don't know a good name for the other 3. If you know any of them, please email me after the talk. In any case, there exists actually a number of machine learning problems that indeed are non-convex and satisfy one of these 4 assumptions. Most notably, matrix completion. As shown by Song and Luo back to 3 years ago, they showed matrix completion satisfies the 3rd assumption, and also dictionary learning satisfies the 4th assumption. Quadratic systems of equations, also known as phase retrieval, they satisfy the 4th assumption here. And actually, 2-layer neural network with the ReLU activation function satisfies the 2nd assumption. So those are results that are actually very delicate to prove, and they are also conditional, meaning that if the data is sufficiently, meaning that these problems do not always satisfy these assumptions, but if the data is sufficiently random, say they are drawn from some Gaussian distribution, or maybe if the data is the so-called incoherent, meaning that the data are widespread into the space, whenever this happens, one can show that these problems satisfy these type of one-point convexity assumptions. Therefore, we can now go to the second question, which is how to design efficient solvers under one of these 4 assumptions. So the answer is that is actually quite easy. That is, let's first grab an analysis for convex optimization. For instance, in convex optimization, we know gradient descent and Sc.D converges in this rate. You opened up that proof and stare at it for 1 minute. Typically, you're going to realize that the proof is not actually using this for any 2 points, but sometimes only using this with respect to X star. And therefore, I claim that the same proof of convergence for gradient descent and Sc.D that sit here actually directly translates into a convergence proof here for the first assumption and gives the same type of convergence rate. So this is not a coincidence. You can go to see, for instance, gradient descent also converges in this rate when the function is smooth, and you can also turn it into a result here. And you can also do it here, 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 here. So that seems to suggest that one-point convex functions are easy to optimize because we can, at least in terms of gradient descent and stochastic gradient descent, we can just open up the proofs on the right and then translate them to the left. So this sounds easy, but I claim that there are also a number of non-trivial questions and even open questions remaining on this slide. Namely, we can also ask ourselves questions like, can we do variance reduction? We know variance reduction, like SVRG, works in all of, whenever the function is convex, and therefore for all of the 4 cases here. But does SVRG work on the left? My answer, so far, like, what we know is that there exists a weak version of SVRG that works under assumptions 1, 2, and 4. So I'm not going to define what weak means, but you can go into the paper of Shalev-Schwarz, in which he gives a proof for the so-called sum of non-convex functions. And if you dig into that proof, you can realize that all he's using is an assumption like this, and therefore, like, this proof also works for one-point convex functions, but it only works under assumption 1, 2, and 4. So a natural open question here is, can we do SVRG for the 3rd case, or can we do the more general version of SVRG at all? That's one open question. The other open question in this line is about acceleration. To the best of my knowledge, the only acceleration result we know under this one-point convexity assumption is here. That is, under the first assumption, we know that for the full gradient version of accelerated gradient descent, it works. And this proof is actually never written anywhere. So Michael Cohen, who is now an intern at MSR, he told me the proof I verified 2 months ago. Our group emailed to Nestrov. He said, I already knew it, but I never published it. And we presume that this is not so hard result, so we do not plan to write it down. But if you're interested, you can ask me maybe by email. But in any case, we know how to do acceleration for full gradient methods in this first case, but we do not know any such similar result for the other 3 cases. So that's another interesting open direction for research. To sum up, in this regime of like one-point convex functions, pretty much proving the convergence rate, like proving that, say, gradient descent converges under these assumptions is easy because it's just classical. But what turns out to be hard is usually to show that the individual problems satisfy one of these 4 assumptions. So it's typically like this kind of proof that becomes the bottleneck for our machine learning applications. So this summarizes the type of research in this regime. So let me now spend all of the remaining time to talk about how to find approximate stationary points and approximate local minima for any generic non-convex function. What I mean here is that mathematically, I only impose one assumption on the function. That is, each fi here is smooth. No convexity assumption. By the way, even the smoothness is a very minor thing because think about it, if you have, say, the ReLU activation, you can replace it with something a bit smooth and it becomes smooth. And therefore, this is a minor assumption. Under this assumption, the first goal here is to find an approximate stationary point, which is the point whose norm of the gradient, say, square, is less than or equal to epsilon. Okay? Notice that an approximate stationary point can be either a local minima or maybe something like a saddle point. But at this stage, let's not distinguish them and only focus on can we get an approximate stationary point with the number of iterations t to be as small as possible as a function of epsilon. So let us now denote by t the number of computations of the gradient of fix as before. And let me state known results. Before 2015, I claimed that there are literally only 2 results. One is Sc.D, the other one is full gradient descent. So Sc.D converges in the complexity t proportional to 1 over epsilon square, and full gradient descent converges in rate n over epsilon. So here, this additional factor of n is because computing the full gradient requires you to go through all the fi's at once, and therefore this complexity is bad in terms of the n dependency, but it's good in terms of the epsilon dependency. So the 2 results are incomparable. This is all we know before 2015. The first improvement was actually to show that the SVRG result, simultaneously by the 2 groups of authors, me and Elad Hazen and Radi et al. From CMU, we showed that SVRG actually converges in this complexity strictly better than gradient descent, with this n to the 2/3 sitting on the numerator. I'm going to describe about this method on the next slide. But this is only the first improvement. The second, and by the way, Reddy et al. Also showed that this convergence rate holds for the Saga method as well as for the Proxima version, but all of them have this n to the 2/3, so I'm skipping them. On the other hand, 2 months ago, Lei, Ju, Chen, and Jordan, they showed that there exists a variant of SVRG that actually sits here and has a complexity 1/epsilon to the 5/3. So this strictly beats also stochastic gradient descent. So in the next few slides, I'm going to introduce you the result of SVRG and what they call SCSG, but it's only a variant of SVRG. By the way, it's not only faster than Sc.D in theory, but they also reported that it's faster in practice for some like low depth convolutional neural network and some fully connected neural network. So you can feel free to go to their paper to look at these plots. Let me begin with the description of SVRG. First of all, remember that I already introduced SVRG in the first half of the talk. That is, it's a method that classically assumes convexity on the functions of Fi and also assumes smoothness. And SVRG divided the algorithm into epochs. I guess you remember this picture. Each epoch, say, of length 2n. And then at the very beginning of the epoch, they define the snapshot, and then they define the gradient estimator like this. So the key observation of the convex version of SVRG states that this variance of the gradient estimator approaches to 0. So that was the main idea behind the convex version of SVRG. Now, any questions? Okay. Now let's go to the math. So in fact, the key lemma behind the convex version of SVRG is to prove that the variance of this gradient estimator in expectation is upper bounded by this quantity. And this quantity, in the convex case, approaches to 0 because as xk and x tilde approaches to x star, then this quantity becomes more and more close to 0. Unfortunately, this is totally not true for non-convex functions because, first of all, we don't even necessarily have the ability to approach to the global minimal. And therefore, even if this inequality is true, by the way, it's not, then even if it's true, then this quantity does not approach to 0. And therefore, we need totally different ideas. It turns out that there exists a non-convex version of the SVRG lemma that is simple to prove and works as follows. It says that the variance of the gradient estimator exists another way to bound it, using the smoothness of the function without using any convexity. And if you bound it this way, we know that the variance is upper bounded by a constant that depends on the smoothness times how much we have moved away from the most recent snapshot. Pictorially, this is saying that if, say, we apply SVRG, we may zigzag a little bit, but if we happen to be very close to the most recent snapshot, in this case, I claim we're good because we get a very small variance. Okay? In contrast, if we apply SVRG and the points happen to move farther and further away from x tilde, in this case, we do not get a good variance bound, but I claim we're also in a good shape. Think about it. If all of these, if we have moved quite far away from the snapshot, it means that most of these gradient estimators are in a probabilistic sense correlated with each other. So they are roughly pointing to the same direction. This means we should have made some non-trivial progress in terms of decreasing the objective value. Indeed, one can actually trade off between these two cases and show that in both cases, we somehow win, and in the end, this trade-off gives rise to this very ugly looking like n to the 2/3 numerator sitting here, and it outperforms. This is the main idea that why SVRG outperforms full gradient descent. Let's now move to this so-called SCSG method. So they made a very simple observation on top of SVRG, but a very crucial observation. if you go to the analysis of SVRG, the final theorem is actually stated in this form. That is, how small the gradient of the output point is less or equal to m. Remember, this is the length of the epoch to the 2/3 divided by t. So if you look at this formula, you can imagine that the smaller m is, then somehow the better performance we get. And this is why if we want to choose m to be a constant times n, and we get n to the 2/3. But unfortunately, we cannot make m to go smaller than m, because at the beginning of the epoch, we have to compute the full gradient of the function, and this requires you to go through all the data like simultaneously, and that increases t, which is the number, the complexity t by an added n. And if you want this n value to be amortized into all the iterations, you need the epoch length to be at least n. So now comes the clever idea from SCSG. They said that instead of computing the full gradient of the function at the snapshot, let's only approximate it by randomly sampling m different functions fi and computing gradient only at those points. For example, if m is 1% of the data, then we can make the epoch length to be actually only 1% of the input, and we only, whenever we compute the gradient at this snapshot, we only estimate it with this with this 1% fraction of the inputs. So if you do it this way, you can imagine that the algorithm still converges, but you have to pay some additional factor, some additional term here. And this is the term that corresponds to the loss that describes how much different this approximation is to the true value of the full gradient. It turns out that this additional loss is a function inversely proportional to m. The underlying reason is non-trivial, but from a very high level, if we have m independent random variables, then if we sample m of them and take the average, then the expectation of the difference between the random variable and the true mean of this random variable, this quantity should actually scale inversely proportional to 1/m. This is the law of large numbers. And it's this same 1/m that actually also showed up here as the error term. Therefore, if you look at this, we can find a good trade-off that makes this quantity go to 1/t to the 3/5. And this is, from a very high level, how Lei et al. Achieved this 1/epsilon to the 5/3 convergence rate for this variant of SVRG. So at this point, I described two methods that respectively have beaten Sc.D and the G.D in terms of finding approximate stationary points. But are these the best things we can do? So I don't know. So this is a major open research direction here that is to prove either these are tight, which I don't believe so, or can we design even more clever algorithms that can converge faster? So at this point, to the best of my knowledge, we don't have any additional result here. But still, we can ask ourselves, if we impose additional assumptions, can we get something that are better? So for instance, there's one paper I'm going to present also 2 days from today, called Natasha, that says if we assume some additional assumption on what I'm going to define to be the strong non-convexity of the function, then we can beat even SVRG. Let us see what this is. So recall that for a non-convex function, we say it is smooth whenever all the eigenvalues of the Hessian are bounded, say, between -L and L. Whenever this happens, we say that the function is smooth. Whenever and we say the function is convex whenever all the eigenvalues are larger than or equal to 0. And we say that the function is strongly convex if all the eigenvalues are lower bounded by a positive quantity. So these are some notions that I have already used, and I'm just putting there to remind you. Now comes the new notion I'm going to define. That is, I say that a function is strongly non-convex if all the eigenvalues are larger than or equal to a quantity that is minus sigma. For instance, this blue curve is 0.2 strongly non-convex. In contrast, the yellow curve is 1 strongly non-convex. So the larger the strong non-convexity parameter is, then the more non-convex the function becomes. And therefore, can we study a good trade-off? Can we study like the performance of an algorithm as a function of sigma? That is, if we assume that each Fi is smooth, and on top of that, if we also assume the whole summation or the whole average is sigma strongly non-convex, then can we do something on this plot? That is, can we design methods that have running time that curves up like this? Because the larger sigma is, then we should expect the algorithm to run slower. So in fact, for the gradient descent and the SVRG methods we have described a few slides ago, they sit here. So these are the methods that do not exploit, do not make use of the non-strongly convex parameters, and therefore, like, they sit here. And the last year, as shown like as a side result in the paper by Carmen et al., they showed that there exists a way to repeatedly apply SVRG so that you can get a curve like this. Meaning that the larger sigma is, then the algorithm, after repeatedly applying SVRG, then it runs, the larger sigma is, then the slower it runs, and this is the curve they get. But unfortunately, this curve does not even match SVRG sitting here. And this Natasha result, which I'm going to talk about 2 days from today, is actually going to get this curve, that it matches SVRG here, but it runs faster whenever we have a better strongly non-convex parameter. So these are, to the best of my knowledge, the only known results that exploit the use of strongly non-convex parameters. And again, I do not believe that these are the best we can prove. So I really hope that this new notion of strongly non-convex parameter can help us to give a better way to compile different algorithms. So not only we compile them, here, but we are now also able to compile them like in the full spectrum of the parameter of sigma. So I hope to see more and more results that try to beat these curves. So this is one type of result under additional assumption that it improves, say, SVRG. So there actually exists another result, also by Carmen et al., also to be presented 2 days from now in the same session as Natasha. They are going to assume, they assumed the second order smoothness, and they obtained a method that outperforms gradient descent. So these are the types of results we can get if we impose additional assumptions. So this summarizes my knowledge about the known results for getting approximate stationary points. Remember, a stationary point can either be local minima or a saddle point. Now let's look at a more ambitious goal, that is to get approximate local minima, which are points whose norm of the gradients are less or equal to epsilon, and also the Hessian are larger, the Hessian have their eigenvalues being all larger than or equal to some parameter minus delta. So delta is a positive quantity, and we want, this is a double approximation, we want both epsilon and delta to approach to 0. This is the goal of finding approximate local minimum. From a very high level, in order to achieve goal number 2, we need to do something very simple. That is to first apply a solver for goal 1 that gives us an approximate stationary point. At this point, we may either be already a local minima, in which case we're done, or if not, then there exists an eigendirection of the Hessian that helps us to further decrease the objective value. So this is called like escaping saddle point, meaning that whenever we are at a point whose norm of the gradient is small, then what we really need to do pictorially is to find a direction that helps us to go like this. Now, in terms of how to achieve this goal, there exist 2 classes of methods. Both of them rely on one additional assumption on the function. That is, not only remember we have assumed the function to be smooth, but this time we also need the function to be second-order smooth, meaning that its Hessian does not change too fast when we move from a point x to y. So this assumption turns out to be necessary in order to obtain any meaningful result about local minima. Because if the Hessian changes like dramatically without any control, then we don't really know that if we are very close to a local minima. Because if currently like we are like curving like this, then maybe if we move a little bit, the Hessian changes dramatically. And therefore, in order to get any meaningful result about local minima, we have to make such an assumption. That is, the function is also second-order smooth. So under these two assumptions, there exist two different types of research that try to find the most negative eigenvector. One type of them does not use the Hessian, and the other type uses the Hessian. So let me explain what I mean here. The first type of results do not use Hessian, and they are based upon the following three observations. Observation 1, randomness helps us to escape from a saddle point. Because if we're currently here, then if we randomly generate a direction in the d-dimensional space, if you use a poly-d number of samples, then one of such directions is going to help us to escape. Observation 1, simple to prove. Observation 2, stochastic gradient descent is a randomized algorithm. And therefore, in a very loose sense, stochastic gradient descent escapes from saddle points. So this is the this result was first shown by Ge, Huang, Jing, and Yuan back to 2 years ago. They showed that stochastic gradient descent, indeed, if you choose the learning rates appropriately and if you make assumptions appropriately, then they indeed help you to find local minimum. And their result actually states like this. That is, they can help you to find a point that has not only a small gradient, but also all of the eigenvalues of the Hessian of the output is larger than or equal to some parameter that is minus epsilon to the constant power. So what they proved is something like epsilon to the 1/8, but somehow the tightest possible result is epsilon to the 1/4. Therefore, their result loses a bit here. At the same time, their number of iterations in this theoretical result has a dependency that is polynomial in terms of the dimension. So this is not very good if you compare it to stochastic gradient descent, in which the number of iterations does not depend on dimension, so it's dimension-free. But in any case, you're now requiring more on the local minimal property of the function, and this is why you need more iterations. So that is one result. Later, this year, a subset of the authors and the new authors together, they proved that there exists another way of making the three observations. First of all, again, randomness helps to escape from saddle points. But two, full gradient descent, which is no longer stochastic gradient descent. So full gradient descent plus random perturbation is a randomized algorithm, and therefore it also escapes from saddle point. So they proved the result of this form. If you allow me to steal a photo from their paper to explain this better, so this is what they showed. So if at some point you're at the saddle point, which is characterized by this picture, then we can try to perturb the point, say by moving uniformly at random in a unit sphere, or in a sphere like with some radius that you control somehow. Now I claim that after perturbation, if you're landing here, you're in a very good shape, because if you continue to apply gradient descent, you can escape from the saddle point. In contrast, if the randomization helps you to go into a point in this green belt, then unfortunately you do not escape from the saddle point very quickly. So indeed, this paper of Jing et al., they showed that the total volume of this green belt is actually so small, so that if you do random perturbation, you're with very high probability going to land in a point that's in the white space. And therefore, this method also escapes from saddle point. So this is the final theorem they proved. So they get a good dependency on epsilon here. In some sense, epsilon to the 1/4 to the 1/4 is a tight quantity, which I'm not going to explain why. So they get the tight quantity here, and they also almost match the number of iterations of gradient descent in terms of finding approximate local minimum, approximate stationary point. So you pay an additional polylog factor, but you can get a local minimum property. So this is another type of result where, again, T is the number of computations of the gradient of Fi. So these are two results that both find the local minimum. But as you see that the algorithms here, one is Sc.D, the other one is gradient descent plus perturbation. They did not use any Hessian information about the function, but they can still provide second-order guarantees. Now let me go to the second type of algorithms, which uses the Hessian. But first of all, how can we use the Hessian? The Hessian is the matrix. It's a D by D matrix. Just computing that requires already D-square computational time. And therefore, it's not nice to explicitly use the Hessian of the function. Fortunately, although computing the Hessian matrix is quadratic time, but computing Hessian vector products are cheap. Meaning that for an arbitrary vector V, computing the Hessian times a vector, this computation I claim is typically of the same complexity as computing just the gradient of the function. Let me give you one example. In neural networks, if we have a size S circuit, meaning that we have S neurons, which describes one of the loss functions Fi, then we know that computing its gradient takes time order S. This is famously achieved by the so-called forward-backward propagation, which is now the foundation of deep learning. But if you think about it, computing Hessian vector products can also be done by forward-backward propagation. In particular, if we define, for analysis purpose, if we define a function gi like this, then the gradient of gi becomes Hessian vector products. And therefore, using the same forward-backward propagation, the same running time, order of S, which is the size of the circuit, you can also compute Hessian vector products. So this is an efficient way to use the Hessian information about an objective function. For this reason, from now on, let me redefine this complexity T. I'm going to define T to be not only the number of computations of the gradients of Fi, but also the number of computations plus the number of computations of Hessian vector products. So at least for neural networks, computing this and that should be of the same complexity up to a constant factor. Now, in terms of this new notion of T, we can see, we can try to find approximate local minima and obtain trade-offs between epsilon and T. Let us first use a naive approach, which might be the first approach that everyone is now maybe thinking about. That is as follows. In each iteration, if the gradient is large, then we try to use gradient descent. As long as the function is smooth, gradient descent guarantees that in each iteration we decrease the objective value by some amount which is proportional to the norm of the gradient square. This means this kind of gradient updates cannot happen for more than 1/epsilon times if you assume the objective value to the global minimum is bounded by a constant. And therefore, it cannot happen too many times, and each time, T, the complexity, increases by n because computing the full gradient requires the computation of the gradient of Fi like n times. And therefore, each iteration, T increases by n, and we cannot have more than 1/epsilon times of reaching this line. Okay? Otherwise, if we know that the gradient is small, then we are at an approximate stationary point. So now we try to detect, do we have an eigenvector whose corresponding eigenvalue of the Hessian is less or equal to threshold minus delta? If we don't, I claim we're done because we already found a local minimum, approximate local minimum with parameter epsilon and delta. Otherwise, then we find it algorithmically, and then I claim that mathematically, if you follow the direction of either plus W or minus W, where W is any vector satisfying this, then we can decrease the objective by at least a quantity that is delta to the third power. So this is tight mathematically. And because of this observation, we immediately know that this step cannot happen for more than 1 over delta cubed times. And I further claim that the complexity for the computation of the eigenvector, if you use the result of Garber et al. From the ICML 2 years ago, then the complexity is n over root delta. And this solver of eigenvector does not need any explicit representation of the matrix. It only needs matrix vector products. And therefore, the number of matrix vector products turns out to be n over root delta. So if you use this result, then you can find a vector satisfying this property in this complexity. Now let us combine these two boxes. In the first case, we have at most this number of computations of gradient descent, and each time with this complexity. So we have n over epsilon. And in the other case, we have this multiplied by that, so we get n over delta to the 3.5. Therefore, this naive approach already gets us to an approximate local minima with this total complexity. So I state that this already improves upon the gradient and the perturbation method, because over there, you have epsilon to the 1 over 4. If you put it there, you get also epsilon to the 1 over 4, but the complexity is only n over epsilon. Meaning that you do not need to pay this. So once you have access to the Hessian vector products, remember this method does not use Hessian, but the one above uses Hessian information. Now using this additional information, you do not need to pay the polylog vectors, and you can get the same kind of local minima guarantees. So in fact, this is only a naive approach, so one can do something more clever. So there exists a way to actually achieve a complexity that's even better. That's n over epsilon to the 0.875, as shown independently by us, Agarwal et al., as well as by Kamen et al. So the first paper is published in this year's Stock. The second paper, I think, is under a journal submission. So these works showed that actually one can do something that's even better than gradient descent plus eigenvector computation, the naive approach, and achieve an even faster running time. So here is a single slide to illustrate how this is achieved. The main idea is to swap the two steps of the naive approach. In the naive approach, we first found a stationary point, then we try to get the eigenvectors. Now we swap the order. We first detect whether or not the Hessian has a negative eigenvector. If it does, then we move in the direction of either plus or minus that vector. We can guarantee to decrease the objective by epsilon delta to the third power. So it's the same argument as before. We have this complexity, and this step cannot happen too many times. Otherwise, if we do not have any eigenvector of this Hessian that is too small, then we're in the blue case. Because all the eigenvalues are at least larger than or equal to some threshold minus delta. So we're in this blue case. So informally speaking, one can start to apply any method that works for the strongly non-convex setting, and that gives you a complexity. I'm not going into the details about why this is the complexity, but basically you gain this factor of delta to the 1/2 on the numerator because of the additional non-convexity of this objective. So using this information, you plug everything together, you can get this n over epsilon to the 0.875 result. And moreover, if you use stochastic solvers to use a stochastic eigenvector solver and a stochastic solver to solve the strongly non-convex function, you can also get this, which is even better than the left-hand side. So this summarizes the two types of research, one using the Hessian information explicitly, the other one does not, and they both can achieve local minima of the function, but one of them gives you slightly better guarantees. So how far can we push the theory? I don't know. We don't have lower bounds yet, and in principle, one can keep pushing this downwards to get even faster algorithms. So let me now conclude the talk by mentioning about a slide for practicality. That is, in practice, can we use the Hessian information like more practically? So if you think about it, the problem of the algorithm that even the naive algorithm I'm describing earlier is essentially doing the following. That is, in each iteration, we're receiving a Hessian matrix, and we can abstract them by matrices M1, M2 until MT. Then essentially, in each iteration, we want to find a vector that goes to the most negative eigendirection of the M's. So this is, in fact, the problem called online learning of eigenvectors. So although we cannot we do not want to find a V that is like exactly at the smallest eigenvalue like of the current matrix MK, but these matrices M are somehow related to each other because you're only moving a little bit far away from the previous matrix if your point like X only moves a little bit far away from the previous point. So to this extent, can we start some regret against a non-stochastic adversary, which we can think about this as an online learning question. So I am, say, an online learner of eigenvectors, and I keep receiving matrices. Now the adversary, each iteration gives me a matrix, and I try to compute what is the eigenvector that corresponds to the smallest possible direction of this matrix. So it turns out that this is also a very interesting problem to study. And if you get any sufficiently practical algorithm for online learning of eigenvectors, then you can plug it in to also help the solvers to get to find approximate local minimums. So we are actively working in this area, and tomorrow I'm going to actually present a paper that solves one case for this problem. So that pretty much concludes my non-convex part of the talk. That is, there are 3 different types of research, and in general, we want to understand, is non-convex optimization really hard? Thank you so much, and